Okay, let's get started with part 5, building instruction for the fire officer. All right, building instruction for the fire officer, um, part 5, for everyone that's taken the building instruction class. Let me get this set up, get the old pointer going. All right, okay. All right, so fire resistive construction. So as I've been saying in all the other parts, we have to look at the structural members of the building. What's the hierarchy of the structural members? And I like to call it, refer to it as, what are the bones of the building? So we need to undress the building to see what's holding the building up. That's going to give us our type of building instruction. So the picture I just presented is a fire resistant building in my response area. It's a 5-story apartment building, right? It has rated stairwells, meaning the stairwells have at least a 2-hour fire resistance rating. It's an area of refuge. You can get into the stairwell. It'll take you outside. It is a safe area. It's also an area where the fire department is going to launch an attack using a standpipe system. Right. This building also has center core construction, elevators. It's separated by wings. Fire doors separate the wings into fire areas using cross corridor fire doors. So what makes this building a fire resistant building? Now, just keep in mind the last part we did was non-combustible. So there was a non-combustible building, but this is a fire-resistant building. So what makes this fire-resistant? Well, the biggest component of this that makes it fire-resistant is the bones of the building, the structural members, uh, they are encased in some type of fire-resistant material. So in this case, in the illustration, we have an I-beam that has sprayed on fireproofing attached to it. So that's going to give it protection against um, direct flame contact for a rated number of hours. So where is this coming from? So fire resistant construction is also known as type 1. And with some of the other constructions, there were some subsets, A's and B's. So with fire resistant construction, we have type 1 construction. It could be type 1A, which means that the bones of the building, the structural members, have a minimal fire resistance rating of anywhere from 2 to 3 hours. A 1B building, structural members have a rating of 2 hours. And this is right out of table 601 in the International Fire Code. So here I just have a little close-up of it. So if you look over here in yellow, this would be type 1, fire resistive. You can see that pretty much the structural members are 3 hours. Um, some secondary members are 2 hours, right? That's type A. We go over to type B, 1B building. Um, it's 2 hours, 2 hours, 2 hours, all right? So it gets a little less. And again, this all depends on we start dealing with the occupancy. What's the occupancy going to be? The size of the building, the number of stories in the building. It's all related to the type of construction that's going to be required. So the difference between fire resistive and non-combustible. Jump over here, we said non-combustible is type 2. So we have the two subsets, A and B. So a non-combustible type A, you have 1 hour fire resistance ratings of some of the structural members. Type B are the construction that we were concerned with in non-combustible because of direct flame impingement on structural steel members and having collapse relatively quickly. There is no fire resistance. It's all zero. So that's the difference between the fire resistive and non-combustible. Some examples of fire resistance. Uh, in this case over here, we have a part of a hospital is under construction. This is a stairwell. You can see the stairwell is block. So you're getting a 2-hour fire resistance rating. The structural steel members, the H columns, and the I beams are all sprayed on fire protection. Up here, we can see the spray on fire protection um, on the underside of the floor decking and on the connections, the bolt connections, the I beams, and the H columns. Other than spray on fire protection, the structural members can also be wrapped in gypsum. So in this illustration, we have a H column and it's wrapped in gypsum. If you go to the gypsum website, or gypsum has cut sheets on how different structural members can be protected to get specific hourly requirements. Columns can also be, the structural members can also be encased in concrete, as shown here. So again, I said in the beginning that fire resistive construction a lot of times is based on type of occupancy, size of the building, number of stories. In this case, I'm showing an example of a I2, which is institutional. It's a hospital medical facility of type 1A fire resistance rating. And when we come into these types of occupancies, we're going to be dealing with issues of evacuation. So we talked about 5A construction, or not, excuse me, not 5A, 1A construction, fire resistive. We deal with a lot of medical facilities. Um, in medical facilities, we're not going to have people are not going to get out of bed and evacuate the building, right? Um, it's more of a shelter in place. So in these type of occupancies, um, the fire resistance rating is high because we're going to create areas of refuge. So in this illustration above here, we have a floor of a medical facility with treatment rooms, and the cross corridor fire protection basically breaks this into two fire areas. So we have a 3-hour fire separation here, and that 3-hour fire separation is maintained by the use of fire doors, right? Which automatically close on the fire alarm system. We also have, in each area of refuge, we have stairwells. Now, the idea here is to, if a fire starts over here, right, in a medical facility, they're going to shelter in place, right? All the room doors are going to be closed. They're going to take action to try to extinguish the fire. Um, if the situation becomes that bad, they're going to move people from this side. They're going to move them to this side, so an area of refuge. And worst case scenario would be the next move is going to be down a flight. So we have stairs here, right? We may have an elevator, right? Elevator could be used if it's determined that it's safe to evacuate patients if it comes down to that. But with the fire resistance, if the fire resistance is maintained here, this area of refuge should suffice until the issue is contained over here. Because remember, we're talking about medical facility. It more than likely, at least newer facilities, are going to be fully sprinklered. So the sprinkler should control uh, just about any fire situation, or at least keep it in check until the fire department can respond and complete extinguishment. So the issue with maintaining this fire compartmentation is everything has to work. So the fire doors have to close properly, right? They have to latch. Here's a picture that I took on an inspection. The ceiling just happened to be open, all right? So when I looked up in there, I could see penetration. So they went ahead and some contractor punched a hole through the concrete wall to run IT cable and other cables. So this 3-hour rated wall now is 0 rated because we can have products of combustion pass right through from this side into this side. So our area of refuge is now violated. So that becomes important when we talk about penetrations and separations, especially in fire-resistant buildings. Down here we have a floor being penetrated by IT cable and electrical cable and conduit. But everything in here is sealed with what they would call a UL listed system. Right. So if you go to the UL website, if you go to the UL catalogs, um, you can look at what type of floor system you're going to penetrate, what kind of material is going to penetrate the floor system, and it give you UL diagrams of, or they give the contractor UL diagrams of how these penetrations are supposed to be sealed up. The amount of material they need, what kind of material they need, and how it's supposed to be done, the actual space that is allowed in the conduit with the wiring or whatever harnesses are going through here. So it is a very technical operation, right? You just can't go down to the local big box store and pick up a can of spray foam and put spray foam in here. That doesn't work, all right? That's no good. So here's a picture of a building where it was still under construction, but we're looking up through the plumbing wall behind the bathtubs. So we're actually standing in the basement, and we can look all the way up to the top floor. So again, this was pointed out to the building inspector to make sure that on his final inspections that all these were sealed up. So again, there's another area of fire spread, smoke spread throughout the building. If you had a fire in the basement or a fire in a bathroom, you have this open plumbing wall, smoke and flame could go up the plumbing wall to upper floors. And we'll see a case study of that in a few minutes. Actually, we're going to look at it right now. So here's the fire compartmentation. So here's a case study, fire compartmentation, smoke spread and fire gas to remote areas. Right, so this was Times Tower, and this is from Chief Mackiniff's book, Strategic Concepts. So in 1961, November, Times Tower, New York, fire was contained to a subcellar. However, 2 firefighters were killed on the 22nd floor from inhalation of fire gases. So when I developed this course, my main concern was not to teach specific building construction per se, but how building construction relates to tactics, relates to fire behavior, all those things. They all have to come together. So I like to say that when I teach the classes, a fire in a fire-resistant building is going to react differently than the same fire in a wood frame building. Fire is a law of nature, so it's going to basically react the same way. The difference is where in the building and the type of construction that's involved is going to affect the way you devise your incident action plan for the different type of construction. So in this case, the fire is contained to subcellar, storage room in a subcellar, maybe some extension to other areas in the subcellar. But the issue is not that the fire is going to extend to upper floors. The problem here is the fire gases have extended well beyond the fire area up into upper floors, possibly through shaftways, through elevator shafts, through other means of extension. And 2 firefighters were killed on the 22nd floor doing searches. Again, excuse me. Anybody familiar with the MGM Grand Fire in Las Vegas? Number of people were killed in their rooms or remote from the fire, and again, it was all due to fire gases, carbon monoxide, smoke travel. So it wasn't the fire that killed them; it was the smoke. So compartmentation is the key, and again, you need to adjust your incident action plan based on the type of building construction you're responding to. All right, second case study, fire compartmentation with fire spread to remote areas. So this was the Schomburg Plaza in New York, and I use this because I recently saw a little article and some video and podcast on this. So I thought this was a good subject to bring up for fire compartmentation. So high-rise building. Um, I'm by no means any type of expert on high-rise firefighting, but I think we need to look at the compartmentation. And again, it doesn't have to be a high-rise building. That first picture I showed you was a 5-story fire-resistant building. Has fire compartmentation. Hospital has fire compartmentation. Could be 3, 4, 5 stories. So it doesn't have to be a major high-rise. But in this case, the fire starts in the basement trash room. Fire department responds. Report of a trash fire. Again, something that they get, all the time. The issue was that in this building, the trash chutes, each apartment had their own trash chute inside the kitchen, right, which is kind of rare, um, from what I've been told. That the trash chutes are usually located out in the public hallway, so you would have to take your trash, go out into the public hallway, go to a trash room or a trash chute that's in a hallway, open the trash chute door and dump your trash in. Um, in this case, the building was built with trash chutes in the kitchens. So we don't know the issue, whether the trash chute door in the kitchen was ajar, it didn't have a good seal, it wore out over time, but the compartmentation wasn't there. The other issue was there was sprinklers in the chute. Every so many floors there were sprinklers. Um, from what I understand, the sprinkler system was shut down a few days prior for maintenance, was never turned back on over the weekend. The fire started on a Sunday morning. Um, it was reported that smoke alarms in the building weren't working. So the fire was located in the trash chute, in the trash compactor room. Fire raced up the steel chute, even though it was an enclosed chute. Um, it exited into one of the apartments, most likely because the compartmentation was breached uh, in the door. Also, again, the chute was designed to be operated with a working sprinkler system. So any fire would have been tamped down by the sprinkler system. So fire should never have gotten into the apartment. Anyway, 3 persons in the apartment were cut off. They either jumped or they fell, attempting to get to another balcony. And then 4 other persons in the apartment were found dead from smoke inhalation. So just an example of compartmentation, even in a fire-resistant building. If there's a cascade of events, um, things can go terribly wrong. So just keep that in the back of your mind as the incident commander if you have a building of this nature in your response area. So going with some of these fire protection systems, passive fire protection systems in fire-resistant buildings. Um, there are buildings that have smoke control systems. Once you get into newer buildings where the atrium or the floor level is more than 3 stories, the atrium is required to have some type of smoke control system. So what we have here is, this is a fan, an atrium fan, sits on top of the roof. This is what it looks like. This is an older building, but it does have the atrium smoke control. So when the fire alarm goes off, this fan kicks on and starts to evacuate smoke from the atrium. The idea is to keep the egress path in the common area clear, so occupants can egress the building through hallways or corridors that are open to the atrium to get to a stairwell, to go down a stairwell to get out of the building. Right down here we have a pressurized stairwell. So this is a fan that is sitting on top of the roof. It does have a smoke detector here. So in this case, when the smoke detector activates, this fan kicks on and pressurizes the stairwell. So the idea here is to keep the smoke out of the stairwell. And again, you can have so many X amount of doors open or ajar, and the stairwell should be kept fairly clear. So this will allow occupants to exit the stairwell. It will also give the fire department an area in which to initiate a fire attack with a standpipe. But again, you need to go out there and you need to know your buildings. I know that that first picture I showed you with that residential building that I have, um, that was designed where when the fire alarm went off in one of the wings, that floor would, the smoke control system, that floor would go into exhaust, and the surrounding floors above, below, and every level would go into pressurization. So basically, keeping the smoke compartmentized to that one wing. So again, you need to know your buildings. So here is a real quick video on stairwell pressurization.
When the fire alarm activates, fire detection system will send a signal to activate both pressurization fan and ANYA control stairwell pressurization system. The system will now monitor the stairwell pressure using differential pressure transmitter install. Typically the transmitter is being attached above the fire exit door. The transmitter will continuously transmit signal to the stairwell controller, then will modulate the damper actuator opening based from setpoint and DPT pressure data. The system will control the pressure to make the exit doors accessible while preventing the smoke to enter the fire exit at the same time.
All right, so that is obviously some new technology that's out there. Um, Many of you may have buildings that do not have a smoke control system. So again, you have to get out there, inspect your buildings, um, and have an idea of what is out there. So here is just an illustration or a quick video on how the atrium fan works to remove smoke from an atrium. So fire in an atrium or anything that is exposing into the atrium, smoke level gets to the smoke detectors, the alarm is set off, the atrium fans come on, and we're going to reduce the smoke level. Um, it's supposed to keep the smoke level at least 8 feet above the highest level of occupancy. So this area up here, the smoke shouldn't come down below this area right here. And you can see the heat plume. So we're keeping this area here clear so the occupants can get to the stairwell and exit the building. Okay, let's see. I have to move on. Okay, fire protection systems. So when we're dealing with fire resistant construction, we're most likely dealing with larger buildings, um, occupancies such as hospitals, high-rise construction, larger buildings of that nature. So in this case, we're going to have fire department sprinkler systems. We're going to have standpipe systems. We're going to have fire pumps. So I just want to touch upon some of these components, just so you have an idea of what you might be looking at when you get out into the field and start looking at your buildings. So to the left is a standpipe and sprinkler fire department connection. So there's numerous fire department connections here, right? Uh, One I believe is for the sprinkler, one is for standpipe. There's signage over here that's going to tell the pump operator or the chauffeur um, what system to hook to if the fire, if he knows the fire is located in a different part of the building. This over here is a fire pump test header. So again, we don't want to touch this. This is only for testing the fire pump. So on the bottom left, we have our fire pump. And we'll go over the components of the fire pump, I think, on the next slide. And below here this is in a stairwell. So we have the standpipe riser, right? And we have a zoned sprinkler system. So this is the 4th floor. It's giving you the stairwell location. This is going to the sprinkler system. Here's the flow switch. And here's your sprinkler riser, or your standpipe risers right here. All right, so fire pumps. Again, depending on where you come from, you may have a lot of experience with fire pumps. You may have no experience with fire pumps. So just to give you an idea of why fire pumps are in buildings, it's all based on hydraulics. So the fire pump we put in a building is basically almost the same fire pump that you have on your fire apparatus. Right? Centrifugal fire pump, more likely than not. And the reason we put the pump there is because when we build a building and it needs a sprinkler system, we look at the municipal water supply curve. So here the black line represents the water supply from the city, and the red triangle is the required water flow for the sprinkler system. So in this case, the municipal water supply does not meet the pressure that's required for that sprinkler system in that building. It could be multiple floor building, you could have an area of bad water, a lot of factors go into that. So in order to get the required amount of pressure and flow, the building owner is going to have to put in a fire pump. So the blue line here represents the fire pump curve. Now, when we combine the fire pump curve with the municipal water supply, we come up with the combined curve, and now the requirement for the sprinkler system is below that water curve. So the water and pressure is adequate for the sprinkler system. Now, talking fire pumps are very expensive, so they're not going to source a fire pump that is going to be basically any higher in pressure or flow than is required. Big issue of dollars and cents with fire pumps. So just because you have a fire pump in a building doesn't necessarily mean it's going to meet the needs of your standpipe system and your high-rise pack that you carry. So the water flow for the sprinkler may not provide adequate PSI for your high-rise pack and your nozzles. We'll show a couple illustrations coming up real shortly. So just a little note on standpipes. Standpipes are required based on building codes. In the most recent edition of the International Building Code, does not require a minimum pressure at the most remote standpipe riser if the building is equipped with a full sprinkler. And the highest floor is not more than 150 feet above the lowest level of fire department access. So the key here is to know your buildings and fire protection systems that are in. So here is just a typical fire pump room. So in this case, we have a fire pump. It's a 1500 GPM fire pump, and it's rated at 40 PSI. So it's a centrifugal pump, right? Here's the pump driver. This is the motor. It's an electric motor that drives the pump. This is a medical facility, so it has a generator backup for the fire pump, for the motor. There's also a jockey pump. Now the jockey pump is going to maintain pressure on the system so the fire pump doesn't constantly kick on. So the jockey pump is going to, um, think of it this way. Any drop in pressure that would be less than the drop in pressure that would be caused by a open sprinkler head, the jockey pump is just going to maintain pressure. If there's a drop in pressure from a open sprinkler head that activates for a fire, the flow is going to be great enough that it's going to override the settings on a jockey pump and the fire pump is going to come on. Zone valves, again, OS and Y valves, outside stem and yoke. This valve is closed, we don't see any threads, and this valve is open, so we see the threads. And again, the length of the stem is going to give you the size of the pipe. So this is appears to be a 6-inch sprinkler riser. And there's a fire pump controller. It's going to look something like this. Again, when you're dealing with fire pumps, if the fire pump is not adequate to support your standpipe operation and your chauffeur hooks up to the fire department connection and is pumping to the system, the fire apparatus pressure is going to be greater than the fire pump, so it's basically going to shunt the water flow from the fire pump. So that means the fire pump is going to be running a churn. So in that case, it's recommended that someone go in and shut the fire pump off, and then just use the fire department apparatus to supply the system. So just talking about high-rise packs, I just want to do a quick analysis, comparison between high-rise packs. I know different departments use different high-rise packs. Again, I'm not a high-rise firefighting expert. I do teach a lot of pump school. There are departments that would use a 1.75-inch hose line with a fog nozzle, and we can see that 150 feet of 1.75-inch hose with a fog nozzle at 100 psi, it flows 200 GPM. So if we had an 8-story building, our nozzle pressure would be 100 psi. We got to deal with elevation, right? Pumping elevation up the riser. The friction loss would be 75 psi. Device approximately 10 psi. So our pump discharge pressure would be in the area of 225 psi. So that's very high. So and then we have to account for any friction loss in the supply hose, depending how remote you are from the riser to the hydrant. So just a comparison, before I go on to comparison, just note here, buildings requiring standpipes, no sprinkler exception. Prior to 1993, NFPA 14, which is the document that covers standpipe operation, standpipe installation from NFPA, it required 65 psi at the most remote riser outlet with 500 GPM available. And that was based on 2.5-inch hose. Excuse me, that was based on 2.5-inch hose with a smoothbore nozzle using an 1.1/8 tip. Now, post 1993, after the One Meridian Plaza fire in Philadelphia, the code changed. Now requires 100 psi at the most remote riser outlet with 500 GPM for the first riser and 250 GPM for each subsequent riser, not to exceed 1,250 GPM. So there was some updates made to that NFPA standard based on 3 firefighters being killed at One Meridian Plaza in Philadelphia. And again, I'm not going to go into the reasons why, the issues with the sprinkler system, the the valves and that type of thing. You can look that up on your own. So again, just a comparison. In this case, we're using 150 feet of 2.5-inch hose with an 1.1/8 tip, smoothbore nozzle, 50 psi, flows 265. Right. We reduced our nozzle pressure, elevation still the same. We reduced our friction loss. All right, device is still the same, and we reduced our pump pressure. So we saved almost 100 psi from the last comparison based on high-rise pack. So takeaway from this is if you have buildings that have standpipes, you need to evaluate your high-rise pack. It may not be a high-rise building, but you may be using a high-rise pack in a low-rise building. Go out there, walk the building, get some measurements, take a look at what the fire flows are required. Maybe you need to evaluate and reconsider some of your high-rise pack operations. Again, just food for thought. Again, we talk about fire-resistant buildings, so we have to talk about concrete construction. So this would be pre-stressed concrete. So pre-stressed concrete is formed off-site. It's cast off-site. Steel tendons basically run through the concrete and are tensioned, and then the concrete is poured over the steel tendons. This gives the concrete its tensile strength. Right? And an issue is the steel cables, if they're exposed to heat, they'll start to fail at 800 degrees. So the picture here is we have this jail expansion, and these things are all precast off-site. Everything's brought in, put in like an erector set. So you can see here, this floor deck is just resting on a corbel shelf here. And again, this is for a jail expansion, but I've seen numerous parking decks built with the same type of construction. And again, in this area, the seismic issues are not what they are in other parts of the country. So I'm assuming that we can get away with this because of the lack of seismic issues. I don't know if this would be a good connection. You go to areas out on a fault line or someplace. But again, you need to know the building codes. You need to know the buildings in your area and your parts of the country, wherever you come from. So again, we can see this floor panel is just resting on this ledger right here. This is a double T precast panel, right? Panels are cast off place. They're brought in, they're trucked in, they're craned up, and they're put in place. So there is steel cable running through all these beams that's been pre-tensioned. It's tight like a rubber band that's been stretched, and then the concrete's poured over it, and then the stretched steel wants to go back into place, and that gives the compression strength on the concrete, which gives it its tensile strength. So here's the steel tendons, the pre-stressed steel tendons. So that if you can see the end, that's what it would look like. So these are all pre-stressed where the forms were made and the concrete's poured over it. So these are under tension. So if concrete is spoiled away and these cables are exposed, if they're exposed to flame, they could start to fail. If you're doing a USAR operation and you're cutting concrete, you're chipping concrete, and you see one of these cables, you need to take a precaution. Do not cut that cable. Again, if you're a USAR team, you want to get a structural engineer in there to have him take a look at it and come up with a plan on how to get through that concrete if that's the case. So again, this becomes dangerous if you start to cut these things. All right, so we got cast on site concrete. So again, down here we have rebar, and again the rebar is going to give the concrete its tensile strength. So the concrete is going to be poured into these forms over top of the rebar, and it's going to be set. It's going to stay there until it's cured. A number of days. It's normally going to be in some type of what they call false work, which would be possibly wood. Again, a dangerous time. If there's a fire in the false work, if there's fire in those wood forms, they start to come apart. Concrete is not cured. you could have possible collapse. Picture up here in the upper left. Here are the cables in this monolithic pour of concrete, and they're getting ready to be what they call jacked. So they're going to be tensioned on site. So the precast concrete was tensioned off site. This cabling is being tensioned on site. Over here is just a picture of once this is jacked, the ends are just mudded up with concrete. So you can see where all these cables, each hole here is where cables are running through. So as I have here, the picture above is a parking garage. The concrete was cast in place in wood forms called false work. Steel tendons are in the form when the concrete is poured. However, the steel tendons are not tensioned until the concrete is cured. This process is known as jacking the tendons. The structure is unstable until the cables are jacked and the concrete is cured. All right. Again, location of the steel cables cast in place in the concrete. I took this off the internet. Parking garage. I think everybody has at least one. All right. So we have a car fire in a parking garage. We can get spalling of the concrete. In this case, this was in the UK. All right. The car in a parking garage can damage the concrete, and any concrete that's dislodged is called spalling. So, and if the tendons are exposed to the fire, they could fail at 800 degrees. Down below here, this was a fire in the UK. It destroyed this entire parking garage. So they had, I don't know, it looks like couple hundred cars were involved. And I do believe the parking garage had to be torn down because it was just unsafe. So some of the tactical points to consider when dealing with fire-resistant construction. Fires and fire-resistant construction pose different problems than fires in wood frame and ordinary construction. Compartmentation, if in place, can aid in fire containment. Automatic suppression systems may be present. Smoke, carbon monoxide, and other fire gases migration to remote parts of the building must be considered. Shelter in place may be an issue to deal with, especially with nursing facilities, medical facilities, places like that where the occupants cannot readily self-evacuate. Even with different types of occupancies, high-rise occupancies, motels, larger buildings, there may be a shelter in place requirement or a shelter in place procedure from the fire department that they only want to evacuate, certain levels or certain floors until they can get a handle on the problem. And again, any of these buildings, there's always a wind-driven fire component that you need to be cognizant of. And this isn't a wind-driven fire class, but there's plenty of videos, plenty of information out there on wind-driven fires in buildings. All right, so this wraps up part 5 of the building construction class. So there's my information if anybody needs it, and we'll see you soon.